NVIDIA DGX Spark versus Mac Studio, the local AI king. The race to build the ultimate desktop AI workstation has officially begun. For years, Apple's Mac Studio dominated conversations around local AI. Thanks to Apple Silicon's unified memory architecture, incredible power efficiency, and surprisingly strong large language model performance, many developers believe the Mac Studio represented the future of personal AI computing. Then NVIDIA changed the game. Instead of releasing another graphics card, NVIDIA introduced something entirely different: the DGX Spark, a compact AI workstation derived from the company's enterprise AI platform. It isn't designed for gamers or traditional PC enthusiasts. It's purpose-built for AI engineers, researchers, startups, and developers who want to run, fine-tune, and deploy large language models locally without relying on expensive cloud GPUs. That immediately raised a question across the AI community. Can the NVIDIA DGX Spark finally dethrone the Mac Studio as the king of local AI? The answer is more nuanced than a simple yes or no. Both machines feature unified memory, ARM-based processors, compact desktop designs, and enough horsepower to run models with tens of billions of parameters. But beyond those similarities, they target very different users. One prioritizes CUDA, tensor cores, and enterprise AI workflows. The other focuses on efficiency, seamless software integration, and an exceptional all-around desktop experience. In this comparison, we'll examine both platforms from the perspective of modern AI development rather than traditional computing. Why local AI matters more than ever. Only 2 years ago, most AI development depended almost entirely on cloud services. If you wanted to experiment with large language models, you typically rented GPUs from cloud providers and paid by the hour. That approach works well for enterprises, but it comes with significant drawbacks. Ongoing subscription costs, internet dependency, privacy concerns, latency-limited experimentation. Today, developers increasingly prefer running models directly on their own hardware. Running AI locally provides several advantages. Complete privacy, zero inference cost after purchasing hardware, faster iteration cycles offline, operation, greater control over custom models, no API rate limits. The rise of tools such as Llama, CPP, MLX, TensorRT, and VLLM has made local AI dramatically more practical than it was just a few years ago. The result is an entirely new hardware category: desktop AI workstations. Meet NVIDIA DGX Spark. The DGX Spark is essentially NVIDIA's attempt to shrink its enterprise AI infrastructure into a desktop-sized machine. Unlike gaming PCs, it isn't optimized for ray tracing or esports. Everything inside the system is designed around AI acceleration. The centerpiece is the Grace Blackwell GB10 superchip, combining a 20-core ARM CPU with a Blackwell GPU that includes 5th-generation tensor cores. NVIDIA advertises up to 1 petaflop of FP4 AI performance, paired with 128 GB of unified LPDDR5X memory in a compact chassis. Perhaps more important than the raw hardware is the software ecosystem. Developers gain access to CUSN, TensorRT, NVIDIA, NAMO, PyTorch, Optimizations, Enterprise AI libraries, containerized AI development. These tools are already the industry standard across research labs and production AI systems. That means code developed on the DGX Spark can often move to larger NVIDIA servers with minimal changes. For professional AI teams, that continuity is a major advantage. Meet Apple's Mac Studio. Apple approached AI from a completely different direction. Rather than designing a dedicated AI workstation, Apple created a high-performance desktop computer that happens to excel at many AI workloads. Its biggest strength is unified memory. Instead of separating system RAM and GPU VRAM, Apple allows both the CPU and GPU to access the same memory pool. This makes it possible to run surprisingly large language models that would not fit into the VRAM of many discrete GPUs. Recent Mac Studio configurations offer up to 128 GB or more of unified memory, depending on the model, alongside Apple's high-bandwidth memory architecture. While NVIDIA emphasizes tensor core throughput, Apple emphasizes bandwidth, efficiency, and tight integration between hardware and software. The Mac Studio also benefits from Near silent operation, outstanding energy efficiency, excellent video editing performance, stable macOS development tools, strong support for MLX and Metal. For many independent developers, these characteristics make it one of the easiest machines to live with every day. Hardware philosophy. Two completely different visions. At first glance, both systems appear remarkably similar. Each is compact. Each uses ARM-based CPUs. Each includes unified memory. Each targets AI developers. However, the design philosophy couldn't be more different. NVIDIA built the DGX Spark as a miniature data center appliance. Apple built the Mac Studio as a premium desktop computer that also performs well for AI. That distinction affects nearly every purchasing decision. If your daily work revolves around CUDA, PyTorch training, TensorRT optimization, enterprise deployment, or NVIDIA's AI ecosystem, the DGX Spark naturally aligns with those workflows. If your workload combines software development, creative applications, media production, and occasional local LLM inference, the Mac Studio remains one of the most balanced desktop computers available. The real battle isn't simply hardware versus hardware. It's ecosystem versus ecosystem. And that may prove to be the deciding factor for most buyers. NVIDIA's expansion of the DGX Spark ecosystem through OEM systems from Asus, Gigabyte, Dell, Lenovo, and Acer rather than only NVIDIA-branded hardware. NVIDIA just made DGX Spark bigger than a product. It's now an entire AI PC ecosystem. For years, NVIDIA's DGX brand represented one thing: premium. NVIDIA built AI supercomputers designed for elite researchers, enterprise AI teams, and hyperscale customers. If you wanted a DGX system, you bought it directly from NVIDIA. That strategy has officially changed. Instead of keeping DGX Spark as an exclusive NVIDIA desktop AI computer, the company is transforming it into an entire hardware ecosystem by partnering with the world's largest PC manufacturers, including Asus, Gigabyte, Dell Technologies, Lenovo, Acer, HP, and MSI. These companies will manufacture their own DGX Spark systems based on NVIDIA's GB10 Grace Blackwell superchip while maintaining compatibility with NVIDIA's complete AI software stack. This may look like a simple expansion of hardware availability. In reality, it's one of NVIDIA's most important strategic decisions since CUDA. From selling hardware to creating an industry standard. When NVIDIA first introduced DGX Spark, many assumed it would remain a niche workstation aimed at AI researchers who wanted enterprise-grade performance on a desktop. Instead, NVIDIA appears to be repeating a strategy that has worked exceptionally well in other industries. Don't manufacture every device yourself. Instead, create the platform everyone else builds on. Rather than competing with Dell, Asus, Lenovo, or Acer, NVIDIA is turning them into partners. That means customers will soon have multiple DGX Spark options with different industrial designs, cooling solutions, storage configurations, pricing, enterprise services, and regional availability, all powered by the same underlying NVIDIA AI architecture. The OEM partners. The growing DGX Spark ecosystem includes major global PC manufacturers: ASUS, Dell Technologies, Lenovo, Acer. NVIDIA's official DGX Spark pages now showcase systems from preferred OEM partners built around the GB10 Grace Blackwell superchip, signaling that these systems are first-class members of the DGX ecosystem rather than unofficial clones. Why this changes everything. The biggest limitation of any new hardware platform is scale. Even NVIDIA cannot manufacture millions of desktop AI systems by itself. Companies like Dell and Lenovo already possess global manufacturing supply chains, enterprise sales teams, government contracts, education channels, local service centers, corporate IT certifications. By allowing these vendors to build DGX Spark machines, NVIDIA instantly gains worldwide distribution without constructing an entirely new PC business. Instead of selling thousands of systems, NVIDIA can potentially sell hundreds of thousands, or even millions, through existing OEM networks. One architecture, many designs. Although each manufacturer can differentiate its product, every DGX Spark system shares the same technological foundation. Core technologies include NVIDIA GB10 Grace Blackwell Superchip Grace ARM CPU Blackwell GPU Unified Memory Architecture NVIDIA AI Software Stack CUDA Acceleration TensorRT NVIDIA NIM Microservices Local AI Development Environment. Developers can therefore move projects between NVIDIA-branded systems and OEM-built machines with minimal friction. A familiar strategy. Think Android, not iPhone. The move resembles Google's Android strategy more than Apple's vertically integrated approach. Instead of one company building every computer, NVIDIA provides the silicon, the software stack, AI libraries, CUDA drivers, developer ecosystem. OEM partners provide hardware, engineering, industrial design, customer support, regional certifications, enterprise integration, sales, and distribution. This separation allows rapid innovation while keeping the AI software platform consistent. Enterprise customers get more choice. Large organizations rarely standardize on a single hardware vendor without considering procurement, service agreements, and support contracts. Many enterprises already have preferred suppliers. Dell Technologies, Lenovo, HP, ASUS, Business, Acer, Commercial. With OEM DGX Spark systems, companies can purchase AI workstations from vendors they already trust while still accessing NVIDIA's AI platform. Better global availability. NVIDIA's own hardware is often difficult to obtain outside select markets. OEM partners solve this problem. Their established logistics networks provide local inventory, faster shipping, regional pricing, business, financing, warranty, service replacement, parts, certified resellers. This significantly lowers adoption barriers for businesses and developers worldwide. More competition means better products. Competition among OEMs benefits customers. Different vendors can optimize DGX Spark systems for different audiences. ASUS could focus on creators and developers. Dell may emphasize enterprise manageability. Lenovo can target commercial deployments. Acer may deliver more affordable entry points. Gigabyte could appeal to performance enthusiasts. The result is a broader range of AI PCs rather than a single reference design. NVIDIA wants CUDA everywhere. The real product NVIDIA is selling isn't just hardware. It's the CUDA ecosystem. Every additional DGX Spark system increases the number of developers writing CUDA applications, training AI models locally, and building software optimized for NVIDIA hardware. That creates a reinforcing cycle. More DGX Spark systems, more CUDA developers, more AI applications, more enterprise adoption, more demand for NVIDIA GPUs in data centers. This ecosystem effect has long been one of NVIDIA's strongest competitive advantages. A bridge between desktop AI and data centers. DGX Spark is designed to let developers prototype AI applications locally before deploying them on larger NVIDIA infrastructure. A developer might build an AI agent on a DGX Spark desktop, test it using local inference, optimize with TensorRT, scale to enterprise servers or cloud clusters with minimal changes. This continuity across desktop, workstation, and data center reduces development friction and accelerates AI deployment. The bigger picture. The OEM expansion is part of NVIDIA's broader vision of bringing AI compute from hyperscale data centers to every desk. Recent announcements also extend the same strategy into Windows AI PCs through the RTX Spark platform, with systems from ASUS, Dell, Lenovo, Microsoft, HP, MSI, Acer, and Gigabyte, highlighting NVIDIA's ambition to make local AI computing widely available. The expansion of DGX Spark beyond NVIDIA-branded hardware marks a strategic shift from selling a premium AI workstation to establishing a broad AI PC platform. By partnering with OEM giants such as ASUS, Dell, Lenovo, Acer, Gigabyte, HP, and MSI, NVIDIA is leveraging existing manufacturing, distribution, and enterprise support networks while keeping developers on a unified CUDA-powered software stack. Rather than competing with traditional PC makers, NVIDIA is positioning itself as the foundational AI platform they all build upon. If this strategy succeeds, DGX Spark could become for AI development what Windows PCs became for personal computing, a common hardware standard available from many vendors, accelerating adoption across developers, enterprises, educators, and researchers worldwide. NVIDIA's GB10 Grace Blackwell Superchip explained the architecture that could redefine local AI computing. For years, Running state-of-the-art AI models meant relying on massive cloud GPUs with hundreds of gigabytes of high-speed memory. Even powerful desktop workstations struggled because they hit a familiar limitation: memory capacity. A model might fit in GPU memory, or it might fit in system RAM, but rarely both without performance penalties. NVIDIA's GB10 Grace Blackwell superchip, the processor powering the new DGX Spark ecosystem, is designed to eliminate that bottleneck. Instead of treating the CPU and GPU as separate devices connected over PCIe, GB10 combines them into a tightly integrated architecture with 128 gigabytes of coherent unified memory, high-speed CPU-GPU communication, and AI acceleration that reaches up to 1 petaflop of FP4 performance. The result is a desktop-class AI system capable of running models with up to 200 billion parameters locally, while two connected systems can support models of up to 405 billion parameters. Why traditional PCs hit a wall? Modern AI models are becoming enormous. A 70 billion parameter model can require tens of gigabytes of memory even after quantization. Models approaching 200 billion parameters often exceed the VRAM available on today's high-end GPUs. Traditional workstations divide memory into two separate pools: GPU, RAM, system RAM. Moving data between these memories over PCIe introduces latency and reduces performance, especially for large language models that constantly exchange tensors between the processor and accelerator. This memory wall has become one of the biggest obstacles to local AI development. GB10 was designed specifically to solve it. The GB10 Grace Blackwell superchip. At the heart of DGX Spark is the GB10 Grace Blackwell superchip, which integrates a 20-core NVIDIA Grace ARM CPU 10 Cortex, X9 25 performance cores 10 Cortex, A7 25 efficiency cores, A Blackwell GPU 5th generation Tensor Cores 4th generation, RT Cores high-speed, CPU-GPU interconnect shared coherent memory architecture. Rather than acting like separate chips, the CPU and GPU behave much more like components of a single processor, dramatically reducing communication overhead. 128 gigabytes of coherent unified memory. Perhaps the most significant innovation is the memory subsystem. DGX Spark includes 128 gigabytes LPDDR5X coherent unified memory, 273 GB/s memory bandwidth, a 256-bit memory interface. Unlike conventional PCs, the CPU and GPU share one coherent memory pool. There is no need to duplicate datasets or AI model weights between system RAM and dedicated VRAM. This enables several practical advantages. Larger AI models fit into available memory, lower memory management overhead for developers, faster iteration during inference and fine-tuning, more efficient execution of complex AI pipelines. For AI developers, it feels much closer to programming a single, unified compute platform than juggling separate memory spaces. What coherent really means? The word coherent is more important than it sounds. In traditional systems, the CPU maintains one copy of data. The GPU often requires another copy. Synchronization is necessary whenever data changes. With coherent unified memory, CPU and GPU see the same memory. Updates are immediately visible. Copies are minimized. Synchronization overhead is reduced. This improves both performance and programming simplicity for large AI workloads. Up to 1 petaflop of FP4 AI performance. The GB10 superchip delivers up to 1 petaflop of AI compute at FP4 precision, a level of performance specifically targeted at modern generative AI inference and development. FP4, 4-bit floating point, represents one of the newest precision formats for AI. Instead of always using FP16 or FP32 arithmetic, many modern language models can operate using lower precision numerical formats with minimal impact on output quality after quantization. Benefits include more operations per second, lower power consumption, higher inference throughput, more efficient use of memory, reduced model size. These characteristics are especially valuable for running reasoning models and large language models locally. Why FP4 matters. Every AI generation has been defined by improvements in numerical precision. FP32 enabled deep learning research, FP16 accelerated AI training, INT8 transformed inference, FP8 powered modern AI data centers. FP4 pushes efficiency even further for appropriately optimized workloads. Because each model parameter occupies fewer bits, significantly larger models can fit within the same memory budget while requiring less bandwidth to process. That makes FP4 particularly attractive for local AI systems where memory capacity is a limiting factor. Running massive models on the desktop. One of DGX Spark's headline capabilities is support for AI models with up to 200 billion parameters on a single system. Examples include advanced reasoning models and large open-weight LLMs from organizations such as Meta, DeepSeek, Google, and others, depending on quantization and deployment strategy. NVIDIA also states that linking two DGX Spark systems over high-speed ConnectX networking enables workloads of up to 405 billion parameters. Only a few years ago, this class of workload typically required multi-GPU servers, or cloud infrastructure, built for agentic AI. The hardware is not designed solely for chatbots. NVIDIA positions DGX Spark as a desktop agent computer, optimized for autonomous and long-running AI agents. Its software stack includes NVIDIA DGX OS, CUDA, TensorRT, NVIDIA NIM microservices, and the open-source NeMo Claw platform for building, evaluating, and optimizing agentic AI workflows. Recent updates also improve inference performance and simplify agent deployment. Typical agent workflows include multi-step reasoning tool calling web retrieval code generation memory management autonomous task execution long-running background assistance. Because these agents repeatedly invoke models and external tools, local execution reduces latency and avoids recurring cloud inference costs. Seamless path from desktop to data center. A major advantage of the GB10 platform is software continuity. Developers can prototype locally, fine-tune models, test AI agents, benchmark inference, deploy the same workloads to NVIDIA-powered cloud or enterprise infrastructure. This minimizes friction between experimentation and production. More than a chip. The GB10 Grace Blackwell superchip is not simply another processor. It represents a different philosophy for AI computing. By combining a Grace ARM CPU, a Blackwell GPU, 128 GB of coherent unified memory, and up to 1 petaflop of FP4 AI performance into a compact desktop platform, NVIDIA is shifting capabilities that once demanded racks of servers into a machine that fits on a desk. Paired with support for very large local language models and agentic AI software, it enables developers to build, test, and iterate on advanced AI systems without relying exclusively on cloud infrastructure. In the next part, I'll cover benchmarks, LLM performance, CUDA versus Metal, Allama, VLLM, fine-tuning, inference speed, power efficiency, pricing, and the final verdict on which machine truly deserves the title of local AI king.